Hello everyone, I'm Norman Wahlberger. This is our second lecture in this presentation of Hamilton's discovery of quaternions, essentially solving the rotation problem, the problem of how to effectively describe rotations of three-dimensional space effectively. In our first video on this topic, we looked at the planar situation, rotations in the plane, and the close connection with the algebra of complex numbers. Today we move up to three-dimensional space and consider rotations about a fixed point in three-dimensional space. So we're going to talk about rotations. We're going to get to Euler's theorem on products of rotations, and we're also going to introduce dot products and cross products. Now there's sort of two different ways we can approach this topic, and they're complementary, but it's interesting to keep them separate. One is a purely geometrical approach, where we think about the physics, the geometry of rotations about a fixed point, often by working with a model of a sphere, which is centered at the point in question. This way, rotations of three-dimensional space can be represented by movements of this sphere. And typically we have an axis, say something like this. It's a line that passes through the center of the sphere and two opposite or antipodal points on the sphere. And then about that axis we can move the sphere. That's a kind of a rotation. So to go from that position to that position is a rotation, for example. Of course, we can change the axes. For example, here's another axis, another kind of rotation. And one of the main problems in the subject is to understand how we can compose or multiply such rotations. All right, so we have this geometrical side of things. We also have an analytic side where we introduce coordinates, typically x, y, and z, and where we use the linear algebra of matrices, vectors, and then associated dot products and other algebraic constructions to help us with the geometry. So although these are very closely linked, one should be aware that there are subtle differences and perhaps even a little bit of tension between the two of them. There's many advantages in working with the analytic approach, but there is also a possibility of a little bit of confusion, because when we introduce coordinates, we are placing distinguished roles to three particular directions in our space, which are not really inherent in the geometrical picture. And this introduction of these three distinguished lines has sort of number theoretical issues that can play a role in connecting these two topics. All right, so let's start by thinking about rotations from a geometrical, intuitive, physical point of view. All right, so we're going to be considering these rotations of three-dimensional space, and we're going to consider these as rigid motions of the entire space which fix a distinguished fixed point, usually called O, the origin. And to illustrate this kind of motion, we're going to often employ the sphere, whose center is the fixed point O. So instead of worrying about how the entire space moves, we're just going to worry about how the points on the sphere move, because that's easier to represent. Now, the distinguishing property of a rotation is that it preserves separation of points on the sphere. So for example, if we have 2 points separated by that amount, then if we rotate, the 2 points that we're going to get are still going to be separated by the same amount. And that's independent of how we actually decide to measure the separation. So in fact, there are lots of different possible ways of talking about how far 2 points are separated on the surface of the sphere. But no matter which way you choose, that's going to be one of the properties of rotation, that it preserves separation. Another important property is that it preserves orientation. So that means that, for example, if you had a little circle on the sphere, and say you had a positive orientation of that circle, maybe a counterclockwise orientation, then if you're going to rotate the sphere, the image is still going to have that same counterclockwise rotation. That's as opposed to a reflection in the plane going through the origin, which has the property that it reverses orientation. So reflections are also an important part of the story, and we'll come to them a little bit later. All right, so a rotation is a particular kind of transformation which has a fixed axis. So there are two opposite points or antipodal points which are preserved by the rotation. Usually the rotation is also described in terms of an angle. So we talk about often an angle or rotation of 2 degrees or 10 degrees or 20 degrees, something like this, or maybe negative 10 degrees or negative 20 degrees. But I would prefer that we don't think about angles. Angles turn to be rather a stumbling block for understanding many aspects of three-dimensional geometry. And I know it's very commonly assumed that rotations and angles are intimately linked, but in fact, theoretically, it's not so. And there are many advantages in avoiding angles and their essentially transcendental nature. So to make that point another way, it's important to realize that a rotation is really a transformation that starts in a certain position and ends in a certain position. And the actual motion from the starting position to the final position is not part of the rotation. So for example, let's put the axis up and down like this, and let's consider the rotation that, in fact, maybe I'll position things so that, say, this blue line here is the equator, and there's an axis, something like that. All right. So a rotation is something that takes the sphere in this position and sends it to this position. All right, I've deliberately moved the sphere so you didn't see how I went from this position to this position. So perhaps I went like this, or perhaps I went like this. Something like that. But the point is that the rotation itself is really determined by the initial position and the final position, and not the actual motion from the initial to the final position. So on our diagrams, we're going to have pictures like this. Our sphere represented by this little picture here. And here it maybe is the axis of the rotation with fixed points like the North Pole and the South Pole, say A and A bar. And we have some rotation which sends, say, that point B to that point B prime, that point C to that point C prime, that point D on the equator to that point D prime. But we'll try to avoid drawing arrows necessarily indicating that we have to actually move in this direction as opposed to going in the other way around. The key point is that this point is sent to this point, and how it actually gets there doesn't concern us. It's useful to mention that angles come from astronomy. And in astronomy there is a very good reason why angles are important. Because the Earth is rotating uniformly on its axis once a day. So everything that we observe in terms of the night sky is moving around us at a fixed rate because of this uniform motion. So in astronomy, angles are completely unavoidable and play a very important role. Surprisingly though, when we're studying the geometry of three-dimensional space, and in particular rotations and reflections and other motions, we don't need to use angles, and often using angles makes life more difficult for us. That's going to be an important idea that will even inform our discussion of quaternions in our next lecture. So one of the main problems in the subject is to describe what happens when we combine rotations. So in other words, we have one rotation about one axis, and then perhaps followed by another rotation about another axis, and we want to consider the composition of those two transformations, one followed by the second. That's a very important practical and theoretical problem. Now there's sort of a special case of this. The special case is when the axes of the subsequent rotations are pretty close together. So for example, suppose that one axis was like this and we had some rotation, and then another axis just a little bit moved from the first one, and then another rotation about that one, and then maybe a third axis also again close to the original ones. So in this case we have perhaps 3 or more axes which are all more or less in the same region of space. In that case, the various rotations that we have can be viewed just on a part of the sphere's surface, a little map of the region around the 3 points, say the north poles of the axes. And then the rotations that we're doing here are approximated by planar rotations in this two-dimensional planar approximation of the spherical surface near those points. So what we're saying here is that if we want to understand composition of rotations on a sphere or in three-dimensional space, probably we should understand how planar rotations work when we have centers of rotation which are not necessarily the same point. So we have a rotation about this point, and then maybe a rotation about this point, and then a rotation about this point. How do we effectively work with products of rotations in the plane about different points? Okay, so there's a nice way of dealing with that, is to recall that a planar rotation can be specified by a pair of reflections. We saw this in our last video, that a rotation corresponding to a multiplication by a complex number of unit quadrants can be thought of in terms of a product of reflections of 2 lines through the origin. So for example here, this is all in the plane now, there's say a center O, and here are 2 lines, let's say L1 here and L2 here. And let's consider the reflections in those 2 lines. Let's call them sigma 1, the reflection in L1, and sigma 2, the reflection in L2. And let's have a look at the composition, sigma 1 followed by sigma 2. In other words, that sends a point x to sigma 1 of x, and then apply sigma 2 to that. What happens to various points? Well, for example, this point A, when we reflect it about L1, we're going to get first this point right here, and then when we reflect that about L2, we're going to get this point over here. So the net effect of this composition is to send A to A prime over here. Suppose we choose some different points, say this point B. When we reflect it in L1, we're going to get some point over here, for example. And then when we reflect that in L2, we're going to get this point B prime over here. And you can try some other points and convince yourself that effectively the composition of these 2 reflections is a rotation. It's a rotation about the point O, essentially of twice this angle, where I can think of the angle is not a measurement, but actually of that geometrical segment. So imagine putting that wedge together with another wedge beside it, and you're getting the size of the rotation formed by the composition of those 2 reflections. So that's a very interesting and important tool in thinking about rotations, that we can break them up as products of reflections, which are in some sense more simple and more fundamental kinds of transformations. Let's start now then by considering the product of 2 rotations in the plane. We have a first rotation about the point A1 called rho 1. That's rotation number 1, rotation around A1. And another rotation, rho 2, around the point A2. And we're interested in describing what happens when we perform rho 1 and then rho 2. And let's suppose that we understand rho 1 in terms of a pair of reflections. The reflection in the line L1 and then the reflection in the line L2. We can symbolize that by this little arrow here. So this little arrow from the line L1 to the line L2 somehow represents this rotation, the combined effect of reflecting in L1 and then following by L2. So that's a rotation effectively of twice that angle about A1. Similarly, this reflection, rho 2, we're going to think about that as being the composition of reflection in the line M1 and the line M2, represented by this arrow, this red arrow. All right, so how are we going to compose this rotation followed by this rotation? Well, the key is to remember that this pair of lines that encodes the rotation is not unique. If we rotate both pairs of lines about A1, say we take the initial one here and we rotate both of them to get two lines like this, then the rotation represented by this pair of lines is the same as the rotation defined by this pair of lines, because this separation between these two lines here is the same as the separation between these two lines here. So the rotation of essentially twice that angle is going to be the same as this rotation of twice the angle there. All right, that's the key kind of flexibility that we have in this kind of description of a rotation as a product of reflections, that we're allowed to in fact rotate the pair of reflections that we're using to define the rotation. So how are we going to use that to help us compose these two? Well, what we're going to do is we're going to rotate this pair, and we're going to rotate this pair in a very special way. We're going to rotate this pair so that the second line, L2, happens to go through not just A1, but also A2. All right, so we're going to take this pair here and we're going to rotate it around. So think about this L2. We're going to move that around so that it's now facing in that direction. There it is there. Then the L1 line will have moved down here, so it'll be in that position. So we can call this L2 prime and this one L1 prime. These are the same lines here after we've rotated them. And similarly with this representation of rho 2, we're going to move that one around so that the first line, M1, also has this property that it's this line right here, that it joins this center to this center. So we're going to take M1 and we're going to move it around so that it's in this position, giving us M1 prime. And then M2 correspondingly will be in this position. So this pair of lines will have moved so that they're now in that position there. So we've arranged it that the new L2 and the new M1, L2 prime and M1 prime, are the same. So the second of the lines at this point and the first of the lines at this point agree. Why is that good for us? Well, because it's going to induce a cancellation of reflections. For the simple reason that if you have a reflection in a line and you do it twice, then the effect cancels out. You reflect in a line and then you reflect in the same line, that's the same as doing nothing. So in other words, algebraically, the rotation R1 followed by the rotation R2 is going to be the composition of the reflection in L1 prime followed by the reflection in L2 prime. That's what rho 1 is. And then rho 2 is reflection in M1 prime followed by reflection in M2 prime. So with this composition business, we sort of read from right to left. So the composition is reflection first in this one, and then in this one, and then in this one, and then in this one. And because these two lines are the same, we've arranged that. It means these two reflections in here cancel. And the whole thing just simplifies to the reflection in L1 prime followed by the reflection in M2 prime. L1 prime was this one, and M2 prime was this one. So the product of the two reflections is over here, same picture, just over here, is the reflection in this line followed by the reflection in this line. These two lines meet at a new point. Let's call it A3, which is this point here in this diagram. And the original points A1 and A2 now don't really play any more of an important role. The two reflections in L1 prime and M2 prime now generate a rotation about A3. And we know exactly what that rotation is. It's the rotation of twice the angle between these two lines, L1 prime and M2 prime. So this is a calculus, or way of computing with planar rotations, purely geometrically in terms of pairs of lines that encode the rotations via reflections. You move the pairs of lines around so that the middle two agree, and then they disappear, and then just the outer two that determine the new rotation. So we've described what happens when you compose rotation rho 1 with rotation rho 2. The first one was a rotation around A1, the second one was a rotation around A2, and now we find that the product is rho 3, the rotation around A3. Now it's proper for me to mention that sometimes something a little bit different can happen. So these two lines, L1 prime and M2 prime that we obtained here, through A1 and A2, in this case they meet at this point A3. It's also possible for those two lines to be parallel. Now if those two lines had been parallel, then there would be no point A3 where they meet. And in fact, in that case, we would not get a rotation as the product. The product of the reflection in a line with the reflection in a parallel line is rather a translation in their common normal direction. Please make sure that you convince yourself of that. In fact, it's a translation by essentially twice the separation between the two parallel lines. In some sense, the center of rotation is at infinity. All right, so that can also happen. So we don't necessarily get a rotation. It could be that the product of two rotations is a translation in the planar setting. This is a very geometrical approach. It's a kind of ruler and compass approach that if you actually had two rotations, you could make diagrams and geometrically, with constructions, find out where the center of the product of two rotations is and what the angle or the amount of rotation about that new point would be by computing these two new lines. It's essentially a Euclidean geometry construction of how to multiply rotations in the plane. This is going to motivate and give us some direction for understanding the more complicated problem of how to deal with three-dimensional rotations. So let's apply what we've learned in the planar case to try to understand rotations of three-dimensional space, rotations of the sphere. So the key point is that a rotation of three-dimensional space can also be described as a product of two reflections about two planes through the origin. So let me illustrate that here with this example sphere. I've taken an equator, this one here now, and I'm taking the north and south poles. There they are. Okay. And we're considering a rotation around that axis. And in particular, I'm going to consider a rotation which is related to two planes that go through this axis. And one of the planes is cutting the sphere along this orange great circle, which goes through our north and south poles, and the other one cutting the sphere along this blue great circle. And I want to consider what happens if we reflect first in the orange plane, followed by reflection in the blue plane. Let's have a look first at reflection in this orange plane. So it's a reflection in a plane, like a mirror image. On the surface of the sphere, this fellow here who's sort of currently facing in that direction, if we reflect him in the orange line, we're going to get that fellow there. That's his reflection. Notice that the orientation has been changed. If he was sort of left-handed over here, he would be right-handed on this side. Reflecting in a mirror changes the orientation. This point here, this little circle, for example, would be reflected to this circle. And we could compute the image of any point. Of course, points lying on the orange great circle themselves are fixed under that reflection. All right, now let's follow that by reflection in this second plane, the plane of the blue line that also goes through the center of the sphere. We're going to reflect in that blue line. Then this point over here, this little figure, will get reflected to this one over here. All right? So we're going from there to there. That's the reflection in the blue line. And similarly, this circle here got first reflected here, and then actually its image was here, not the one over here. That's a mistake. So the reflection in the blue one here is there. And then the net effect is to send this little circle rotated to here. So overall, the combined effect of reflection in the orange plane followed by reflection in the blue plane is to rotate the sphere. Rotate the sphere by essentially an angle which is twice this angle between these two lines. And when I say angle here, I probably should use a different word, but twice the separation contained by these two lines. Okay? So a vector like this is not going to be sent to there, but it's going to be sent to there. The north and south poles remain fixed. So this is a way of representing a rotation of the three-dimensional space as a product of two reflections in planes. And just as in the two-dimensional situation, these two planes are not really canonical. They can be moved. They can themselves be rotated. So if we rotated both of them around this axis, we would get a new set of pairs of planes which would generate the same rotation that we started with. So in terms of our picture, here's a two-dimensional representation of that. So here's our sphere. Here's a north pole and a south pole, and there's an axis of rotation through those two poles. And we've shown the equator of that axis as well. So the plane of that equator is perpendicular to the axis that we're rotating around. Okay, and we're going to suppose that our rotation that we're considering is generated by two reflections about planes. And the first plane, say, is given by this great circle here. Okay, and let's call that C1. That's a great circle on the sphere. It means that it's the place where the sphere meets a plane that passes through the center of the sphere. Not just any old plane, but a plane that goes right through the middle of the sphere. That cuts out a great circle. These are the biggest circles on the sphere. And we have a second such plane represented by this great circle here, going behind the sphere and coming out like that. And that's C2. So those are our two great circles. So what we're doing is we're considering the rotation that's the product of reflection sigma 1 in the first circle C1, followed by sigma 2, the reflection in the circle C2. That's our rotation. We're going to call it rho. And let's make sure that we see what it's doing. So for example, this point A, when we reflect it in the first great circle, we maybe get a point like this. And then when we reflect that in the second great circle, we get a point like that. So the cumulative effect is to send this point A to this point A prime. But again, there's no requirement that the point is actually sent along this curve. You can also think of it as having walked around the backside of the sphere, or in fact traversed any old path to get from here to here. The crucial thing is only that we're starting here and ending here. What about, say, the point B over here on the side of the sphere facing us? If we reflect first in C1, we're going to get this point over here. And then when we reflect that in C2, we're going to get a point B prime over there. So the cumulative effect is to send this B to this B prime. And that's a rotation of the sphere, again by essentially twice the separation of those two lines. So how are we going to describe geometrically that rotation? Well, one way would be to describe it by specifying the two great circles on the sphere. But there's a little bit more efficient way of doing that. And that's to use this equator, which is another great circle, perpendicular to both of the great circles that we've just been considering. So the first circle, C1, has itself a perpendicular axis direction. So if we think of the plane C1, it has a perpendicular axis which meets the equator at some point. Let's call it P1. Okay? So this point P1 is the point on the equator which is like the North Pole or South Pole if we think of this C1 as being a new equator. Similarly, if we think of C2 as being some kind of new equator, then it has a north and south pole. And these are going to be, say, this point and this point over here. That line would be perpendicular to the plane that we used to cut out C2. And those 2 points are going to also lie on the original equator, which is the equator corresponding to the north and south poles where the 2 planes C1 and C2 meet. So how are we going to represent this combination of reflections? We're going to do something different than we did in the planar case. We're not going to use the 2 lines or the 2 great circles passing through our North Pole. We're going to rather use these 2 points, P1 and P2, on the equator of the axis of rotation. So there's P1, there's P2. You might say, well, which P1 are we going to use? There's actually 2 of them. And which P2 are we going to use? There's also 2 of them. That's right. So we're going to choose one of these P1s. It doesn't really matter. And we're going to choose the P2 which is closest to the P1. One of them will be typically a little bit closer on the equator than the other. And so the shorter arc, we're going to use that as the arc to represent this rotation. And we're going to actually draw a little arc in red on this equator joining P1 to P2. And that little arc will contain the information of this rotation. In fact, what the rotation ends up being, it ends up being a rotation by essentially twice that arc with this as its equator. All right, so there's quite a lot in this diagram. It's much easier to visualize if you get yourself a ball. It could be a soccer ball, basketball, a globe, beach ball. Get some kind of ball and try to essentially recreate this picture and make sure you understand where all the various points are. Okay. It's a bit complicated but a very rich picture, and it's sort of an interesting and non-intuitive idea that we're going to represent this rotation about this axis here by these 2 points, so this little vector joining these 2 points on the equator of that rotation. And we have some flexibility about doing that because we can rotate these 2 points along the equator where we can put them wherever we want along the equator. As long as they're separated by the same amount, they're going to represent the same rotation. So to come back to our original picture here, I guess we had this story like this where we were rotating about the north and south pole here. We were rotating that to send this vector over to somewhere place like that. Right? To go from here to over there. Right. And so we're thinking of that as being the composition of the reflection in this plane followed by the reflection in this plane. So how would we represent that? Well, we could take our first plane, which is the orange one, and find a normal to it. So the north pole, essentially, of that great circle. Maybe that one, I'll make it big. That would be the first one there. All right? And then we're going to look at the second plane, which is the blue plane. It also has a north pole and a south pole. Maybe that one there I'll choose. Okay. That's the north pole for the blue line, and that's the north pole for the original orange line. And then the representation of the rotation that we're considering is this point and this point followed by, connected with a vector. Okay, so that vector joining that point to that point on this equator represents the following rotation. It represents the rotation by essentially twice this amount. So, something like that. And it doesn't have to be this vector. We could move this vector over. So I could move it over so it's, say, between here and roughly an equal amount, say over there. Right. So this vector on the sphere would represent the same rotation as this vector. They would both represent the rotation by essentially twice that separation with this as the axis. That's a geometrical way of representing rotations of three-dimensional space by spherical vectors on the surface of the sphere. Vectors which lie on great circles, essentially on the equatorial great circles of the rotations we're considering. So now we can use these rotation vectors for rotations to actually describe the composition or the algebraic structure of rotations of three-dimensional space. And we can do so in a very geometric and direct way, which is completely analogous to what we were doing in the planar situation, even though the objects that we are using are a little bit different. All right, so here's how it works. We have two rotations of our sphere or space, and they're represented by these two rotation vectors, rho 1 and rho 2. All right, so rho 1 is the vector which is lying on this equatorial great circle. That's an equatorial circle for the rotation rho 1, which actually rotates by twice that separation. So it would send this point to that point there. Okay, so rotation with this as the equatorial direction, and the axis would be somewhere like this. And then we have a second rotation represented by this little vector, which is also lying on a great circle between this point and this point. And that represents a rotation with axis in that direction somewhere, essentially through twice the separation here. So it would send this point to a point around the other side. All right, so these are the objects that represent the two rotations. And to combine these two rotations, we're going to rotate both pairs so that the final point of rho 1, this one here, and the initial point of rho 2, this one here, match up. All right, so we're able to do that because this rho 1 vector represents the same rotation as the one that we would get by removing that, sliding it down so it would be in that position there. All right, so I'm going to slide this vector down till it's in that position there. It still represents exactly the same rotation as before. It's just it's now in a different position along its equator. And I'm going to slide this vector, rho 2, along its equator so that its initial point is at the same place where the final point of rho 1 is, where the two equators meet. And why does this help us? Well, it's because the rotation rho 1 that we're talking about can be thought of in this way. The rotation is a product of two reflections. And the reflections are the reflection in the plane which is perpendicular to this point. So this point here has an axis coming out from the center of the sphere. And there's a perpendicular plane to that direction from the center of the sphere, which determines a great circle. That's the first reflection that's involved in row 1. And the second reflection is the one in the plane perpendicular to this point. So the combination of row 1 and row 2 is reflection in plane perpendicular to this point, followed by reflection in the plane perpendicular to this point. And then row 2, reflection in the plane perpendicular to this point, followed by reflection in the plane perpendicular to this point. And just as in the planar case, those two intermediate reflections cancel because they're the same reflections. We've cooked it up so that they are the same. So the product reduces to just a product of two reflections in planes perpendicular to points, namely to this point and to this point. So the composition of these two rotations ends up being the rotation determined by reflect in this point, actually reflect in the plane perpendicular to this point, followed by reflecting in the plane perpendicular to that point. And that's given by the vector on the great circle joining these 2 points. So that's the algebra. You take a spherical vector like this, you move it down, and you move this one across so that they're lined up just like an addition of vectors in the plane. And we're kind of adding these vectors just as we do vectors in the plane, except it's all happening on the surface of the sphere. So we get this vector plus this vector is this vector here, which I haven't shown here, but here it is. And that corresponds to this rotation times this rotation is equal to this rotation. So we see that geometrically, rotations can be thought of in a very, very simple way if we are happy to use these spherical vectors lying on the sphere. And if we're happy to agree that rotating a spherical vector along its own direction doesn't essentially change it. All right, that's an interesting kind of algebra. So we end up expressing the product of rotation row 1 with row 2 as the rotation row 3. And notice that special kind of thing that happened in the plane where we ended up getting two lines which don't meet. It's not going to happen here. Because on the sphere, any two great circles are guaranteed to have an intersection point. Get a sphere, play around, convince yourself this works. So great, we've basically given a demonstration of this important theorem going back to Euler in 1776, which is that the product of two rotations is a rotation. In other words, if you take your sphere and you take any axis and you perform one rotation, and then you take some other axis at random and you perform another rotation, then that composite transformation, going from some initial position to some other initial position, is actually a rotation. Somewhere there's an axis so that you can essentially get back to where you started just by rotating around that axis. It's not entirely obvious that that's the case. And Euler realized that it had to be proven, and he proved it. And so basically we've given a geometrical demonstration of that fact using this idea of spherical addition of vectors on the surface of the sphere. Okay, so that's all very geometrical with pictures and models and so on, which is great. But there's also a need for having an analytic approach where we use coordinates. And this is a more familiar approach, I suppose, because people are very familiar with linear algebra. If you've done any mathematics at the university level, you've probably taken a linear algebra course. If you haven't and you'd like to learn some linear algebra, may I recommend my series, Wild Lin Alg, which lays out linear algebra in a more geometrical way than most courses. And it's ongoing, and so in fact, the second half of this course, which is going to be starting soonish, we'll be talking a lot about the kinds of things that we're talking about today, and we'll give a lot more detail and derivation. So if you're interested in this kind of thing, check out this series, especially the second half. Of course, you should have already watched the first half before you watch the second half. Okay, so we're going to introduce some basic things from three-dimensional space. In particular, first, coordinates. So we have an x direction, a y direction, and a z direction. These are three mutually perpendicular lines. You can think of the y direction being in the plane of the board, the z direction as being in the plane of the board, and the x direction coming straight out. It's just that you're sort of over there somewhere and you're looking at it in that direction so that the x direction appears something like this to you. Then we use these coordinates to specify the position of any point in space. So the point P with coordinates A, B, C is that point whose x coordinate is A, whose y coordinate is B, whose z coordinate is C. And it's best thought of in terms of a box whose sides are parallel to these axes. And here's the box here. Kind of going A in the x direction, B in the y direction, C in the z direction. That's the point A, B, C. All right, so what we want to do is we want to apply some metrical considerations to this three-dimensional space. So we want to take planar notions that are metrical and extend them to three-dimensional space. So the fundamental planar notion is the notion of quadrants. Okay, so if you have, say, consider the vector or the segment from 0 to this point R here, which is just in the plane, has coordinate A and B, then its quadrants, the quadrants between O and R, is A squared plus B squared. Notice that we're using this quadrants and not its square root. Square root would usually be called the distance or the length. Okay, we want to avoid that because taking a square root is a transcendental operation. It's usually called algebraic. It's not algebraic at all. It's actually a transcendental, infinite process that never stops. You can't actually complete a calculation of a square root. It's just the reality of things. We want to avoid that. That's too complicated. Quadrants, A squared plus B squared, very nice and simple. How do we extend that to three dimensions? Well, once we have the quadrants here, there's another sort of right triangle going up C. So we have a quadrants of A squared plus B squared here, a quadrants of C squared here, because the coordinate is C, so the quadrants is C squared. And so Pythagoras' theorem applied to this triangle here tells us that the quadrants between O and P should be the quadrants between O and R, which is A squared plus B squared, plus the quadrants between R and P, which is C squared, for a combination A squared plus B squared plus C squared. So we are extending the definition of quadrants to three dimensions. We can define the quadrants of a vector A, B, C to be A squared plus B squared plus C squared. So motivated by Pythagoras' theorem, we can define this to be the quadrants of a vector, and that's the fundamental metrical notion in three-dimensional space. The next important notion is perpendicularity. How do we tell, or how do we define what it means for two directions to be perpendicular? All right, we'll work in the language of vectors. So suppose we have one vector v1, and so the vector is now actually something with a start and an end. So it's a directed line segment. I denoted with round brackets because it's subtly different from the point with square brackets. So when you see round brackets, I'm usually talking about a vector. So we have vector v1, x1, y1, z1, another vector v2, x2, y2, z2. And we want to ask, well, when are these perpendicular vectors, like these ones? Well, if we look at this triangle here, in vector form, if this one's v1 and this one's v2, then that vector will be v2 minus v1. And if we have perpendicularity here, then we expect that Pythagoras' theorem should apply to this triangle, which means that the quadrants of v1 plus the quadrants of v2 ought to be the quadrants of v1 minus v2, or v2 minus v1. It's the same. So what does this equation relating the three quadrants amount to in the coordinates? Well, quadrants of v1, we've defined it to be this. Quadrants of v2, we've defined it to be this. And the quadrants of the difference, well, we have to take the vector, which is the difference of the coordinates, we have to take the sum of the squares of those coefficients. So this equation represents perpendicularity in space if we want Pythagoras' theorem to be true. And we want Pythagoras' theorem to be true in 3 dimensions, just as it is in 2 dimensions. So fortunately, this equation, it appears rather long here, but there's a lot of cancellation once you expand the right-hand side. Because the x1 squared will cancel with that, and the x2 squared will cancel with that. The only thing that will be left on this side, after you divide by 2 and maybe take out a minus sign, is the expression x1 times x2 plus y1 times y2 plus z1 times z2. And that's got to be equal to 0, because that's all that's going to be left on the left-hand side. So I'm showing you now that if you want Pythagoras' theorem to be true, then you want this relation to hold between the coefficients of v1 and the coefficients of v2. This is a very important expression in the coefficients of v1 and v2 for exactly this reason. Okay, this is the reason why this is important. Now, courses in linear algebra just sometimes introduce this and say, well, here's the dot product. We're just going to define the dot product without telling you why you want to know about the dot product. Okay? So I'm telling you why this is important. It's important because it's going to guarantee that Pythagoras works in this situation. So here's the definition. v1 dot v2 is x1 x2 plus y1 y2 plus z1 z2. And this is a number. So given 2 vectors, we get a number, and that number has different names. Sometimes it's called a dot product. Sometimes it's called an inner product. Sometimes it's referred to as a bilinear form. All valid names for it. Very important object. And basically we've established that 2 vectors are perpendicular precisely when v1 dot v2 equals 0. Where perpendicularity is essentially Pythagoras' theorem. Of course, you could, if you don't want to introduce Pythagoras, you could say, well, we're just going to introduce this, and then we're going to define this to be perpendicularity, and then you could prove Pythagoras' theorem. That's also a reasonable approach. Maybe actually cleaner algebraically. Okay. But it's important to realize the motivation for this is because of this computation linking Pythagoras and the bilinear form. Now there's another important construction that we can do with vectors in 3-dimensional space that we can't really do with vectors in 2-dimensional space, or in fact very easily with vectors in any other dimensional space. Something special about 3 dimensions, the world in which we live in. And that's the cross product of 2 vectors. Here's the definition. So we again have vector v1 and v2 with coordinates just as before, and we're going to define this particular combination. And this time I am just going to pull it out of the blue, but I'm going to explain why in a second. All right, so it's a new vector. So the cross product of 2 vectors is a vector. Not a number like the dot product, a vector. And it has 3 components, and they are, and the first component is y1 times z2 minus y2 times z1. And then the next one is sort of obtained cyclically from this by replacing y's with z's, z's with x's, and x with y's. All right, so we get z1 x2 minus z2 x1, and then replace z's with x's, x1 y2 minus x2 y1. All right, so for those of you who know some determinants, you can write this in terms of a determinant, and it's another vector. And it geometrically has the following properties. That if, say, there's the vector v1 and there's the vector v2, that v1 cross v2 is a vector perpendicular to both v1 and v2. And furthermore, its quadrants is intimately connected with the area of the parallelogram formed by v1, v2. So the bigger that area is, the wider v1 and v2 are apart in some sense, then the bigger the cross product is going to be. So I'm going to just state a few properties linking the dot product and the cross product. These are pretty familiar formulas in the linear algebra course, and in the Wildland Algebra course we were going to talk more extensively about these and other properties of the dot product and cross product. So the first is that V1 cross V2 is really perpendicular to both V1 and V2. And it's going to be an exercise for you to check that. So what you have to check is that when you take the dot product between this one and this one, you get 0. And when you take the dot product between this one and this one, you get 0. That's what perpendicularity means in the linear algebra context. The second property to check is that if we change the order of the vectors, then the cross product changes by a sign. The next thing is that it's bilinear, so that V cross U plus W, for two different vectors U and W, is going to be V cross U plus V cross W. And then there are some more fancy, interesting properties of the cross product. The first is Jacobi's identity, which is that V cross U cross W, now that's going to be another vector, because U cross W is a vector, and you're allowed to take the cross product with a vector and that one. So that combination plus U cross W cross V plus W cross V cross U, they all amount to 0. Maybe I should say the 0 vector. Another is that the quadrants of V cross U, so if you take the quadrants of this vector, you're getting the quadrants of V times the quadrants of U minus the dot product V dot U squared. It's a very important formula, sometimes called Lagrange's identity or closely associated with Lagrange's identity. And then there's a generalization of this, which is that U cross V dot W cross Z, when we have 4 vectors, can be written as U dot W V dot Z minus U dot Z V dot W. You might like to think why this is a generalization of that. Alright, so these are exercises for you to do to practice your algebraic skills. And many of you will have learnt about dot products and cross products and connected them with angles, formulas involving sines and cosines. May I humbly suggest that you not think in that direction? Okay? That is not really going to help your ultimate understanding of this subject. I'm sorry to say, but I must say that. Okay? The cosine and sine business is a way of introducing transcendental aspects where they don't properly belong. Okay, so this is a purely algebraic story. That's the way God meant it to be. Okay? It's purely algebraic. High school algebra just rolls out if you do it in the right way. Okay, of course there's a lot more to be said about the dot product and cross product, but this is enough of an orientation to prepare us for understanding and appreciating Hamilton's discovery of quaternions. And there's a lot of interesting twists to this story, that in Hamilton's time, this notion of dot product and cross product was not around. It's very familiar to modern students, especially if you've taken some linear algebra at university level or some physics, because these notions are very important in physics. But in Hamilton's day, they were not around. And his discovery of quaternions, in fact, ultimately motivated people to think about the dot product and cross product, which are intimately connected with the algebra of quaternions, and ended up replacing quaternions in people's mind. But not before a long battle ensued between the proponents of quaternions and the advocates of the vector calculus that I'm describing here. So the history is quite interesting. So in our next lecture, we're going to talk about Hamilton's discovery of quaternions. So we're going up to 4 dimensions now. 2 dimensions first, now 3 dimensions. Next time, 4 dimensions, this beautiful algebraic structure that sheds a lot of light on what's happening here in 3 dimensions. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.